Alright, this crossword will be part of your homework. It is an application type question. It's not just busy work. The fact that each one of these are application questions and the fact that you're given so many spots to fill in the word actually assures you actually are working with your vocabulary. At the bottom, patterns and electron configurations. If you struggle with the electron configuration and can't remember how to do it, always go back to Unit 2A. It's all there. So what you're going to be doing is integrating your information about electron configurations and your information about the periodic table. So for instance, the first one, which families have an s orbital as the last orbital? There's only two families, the alkali metals, get smaller, the alkali metals and the alkaline earth metals. Okay. So as you work through these, you're going to be applying your information about electron configurations. All right, this video is part of your homework. What is an ion? Okay. Make sure you come back and watch that. An ion is a charged atom or a molecule. It is a charged atom or a molecule. It is charged because the number of electrons does not equal the number of protons. An atom can acquire a positive charge or a negative charge depending on whether the number of electrons in an atom is greater or less than the number of protons. So we can have a positive charge or a negative charge based off of the number of electrons. If the atom has more electrons than protons, it is a negative ion. It has more negatives than positives. And a name for a negative ion is anion. Which a way to remember that is anion is a negative ion. Divide the word into A and N. A in ion, a negative ion. It has more electrons than protons. The other one, if I have more protons than electrons, then it's a positive ion, and it's called a cation, because cations are positive, because cats have paws, so they're positive. So they're positive. So in a neutral atom, we have the same number of protons and electrons, and here would be a Bohr description of that. If we look at the number of each of the protons, neutrons, and electrons in here, we have 1, 2, 3, 4, 5, 6 protons. I'll zoom in. We have 1, 2, 3, 4, 5, 6 neutrons. And we have 1, 2, 3, 4, 5, 6 electrons. So my overall charge here is 0. My numbers of positives and negatives are equal, so I have no charge. But the element, how would I determine the element? From the protons. If I have 6 protons, I have carbon. So we look at the next one. The next one has 1, 2, 3, 4, 5, 6 protons, 1, 2, 3, 4, 5, 6 neutrons, and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. 6, 6, and 10. So my overall charge, I have 6 positives and 10 negatives. Overall, I have negative 4. Now to identify my element, I look at my protons, I have 6, it's still carbon. Now if we look at this last one, I have 1, 2, 3, 4, 5, 6 protons, 1, 2, 3, 4, 5, 6 neutrons, and 1, 2 electrons. 6, 6, and 2. My overall charge, I have 6 positives, 2 negatives, is a positive 4. And you do need to indicate that positive. You need to know if it's positive or negative. So it is a positive 4. The element, once again, is carbon. So what we've shown here is carbon as a normal neutral atom, and then again as an anion, and again as a cation. Carbon can just as easily become an anion as a cation because it can gain or lose 4 electrons in order to try and have a full outer shell. You're going to come back and fill in these blanks using these words here. But I do want to go over this picture with you. This picture is very important for what we've been talking about with manipulating atoms. The first one we talked about was what happens if we add or subtract a proton. We're going to create a new element. The next one we discussed is if we add or subtract a neutron. In that case, we create an isotope. If I add another atom to my atom, I get a molecule. And then what we just learned is my new one. If I add or subtract an electron, an ion. All of these can be done to one atom. Okay? And we could do more than one at the same time. A number of neutrons and the number of electrons could be different from the most stable neutral atom. So these are independent changes to the atom.
You do all of them too.
So in the little devil, little angel analogy, think back to Emperor's New Groove. Emperor's New Groove has several references to this. Okay? So on the Emperor's New Groove, they use this. Often consciousness is represented as an angel on one shoulder and a devil on the other, each attempting to lead you to make positive or negative choices. As long as there are one of each, they are supposed to have a neutral influence, and you end up making the decision on your own. However, imagine if you gain a devil. You now have more negative than positive influences, and therefore you will make negative choices. Oppositely, if you lose a devil, you now have more positive than negative influences, and therefore you will make more positive choices. This situation is directly analogous to gaining and losing electrons, and the resulting positive and negative charge. Now notice how I am only discussing gaining and losing negatives. It's because an ion is the same atom, the same element, with different numbers of electrons. If we tried to change the protons, now we've created a whole different element. So an ion is only a change in electrons. If you're talking about an ion, that will only be a change in electrons. Now how do we write an ion? Well, we use the symbol, and we use a sign showing the overall charge above it as a superscript. So for example, hydrogen ion is H+. This positive charge means that there is one more positive, one more proton than negative electron. Considering that neutral hydrogen only has one proton and one electron, in order for it to have this positive charge, it must have lost its one electron. Okay? So in order to become positive, you must have lost electrons, because we're not talking about changing our protons at all. If you're positive, you lost electrons, so now you have more protons than electrons. If you're negative, you gained electrons, because now you have more negatives than positives. So if an atom is a neutral atom, does it mean it is stable? Not necessarily. Okay? Neutral just means an equal number of protons and electrons. That doesn't mean that it is stable. So, blank is used to describe balanced charges. Neutral is used to describe balanced charges. Blank is used to describe the likelihood that an atom will react. That is the opposite. That is stability. Stable atoms have a full outer shell of electrons. Okay? Stable atoms have a full outer shell of electrons. That's what we're talking about when we talk about something being stable. Therefore, only one family of atoms is both stable and neutral, the noble gas family. Also, the more full shells an atom has, the more stable it is. Therefore, the most stable atom from the most stable family is, and yes, this one is not in your word bank, radon. It's in the most stable family and has the most shells. So this right here is crucial for you to understand this concept of stability. It is the lack of stability, or the lack of a full valence shell, that leads to the creation of ions. Unstable atoms, those without a full outer shell, will react with other atoms in an attempt to. So an unstable atom is going to react with other atoms because when they do so, they can gain electrons to fill their outer shell, or they can lose a few electrons, so that way the previous shell is a full outer shell. Okay, so let's look at this picture. Actually, I'm going to highlight this with you first, because this is some very important concept I want you to be looking over. Okay, it's the lack of a full valence shell, or the lack of stability, is why we have ions. Unstable atoms, meaning those without full shells, will react with other atoms in an attempt to either gain electrons to fill the outer shell or lose electrons so the previous outer shell becomes their valence shell. So if we look at this picture here, what we have here is 3 versions of sodium. Right smack dab in the middle, we have regular sodium. Okay? 2 on the first shell, 8 on the second shell, 1 in the third shell. This 1 would be in your S part, so 1s1. Now, while this is neutral, this one's not stable. It does not have a full outer shell. Okay. So if I look here at Na positive, Na positive has a full outer shell. How? Because it must have lost this one. This is my normal. It lost this outer electron, which means that the previous shell is stable. So now this one's stable. Over here at Na7-, it also has a full outer shell, 2, 4, 6, 8 valence electrons. It becomes stable because it gains 7 electrons and ends up with a 7- charge. Okay. So right here, one of these 4 statements is going to be correct. Na positive is more stable than Na. Na positive is more stable than Na. This one has a full shell, that one does not. So we know that one's correct. Let's check the others, maybe more than one. Na positive and Na are equally stable. Well, I couldn't have chosen the first one and the second one. The second one, that would make no sense. And also, this one has an outer shell and that one does not. 1 on its outer shell. So this one is not. Na positive is less stable than Na. Definitely not. So the first one is your answer, and you need to explain why. You're given several lines, fill them up. For the next one, Na is more stable than Na7-. Not going to happen. Na and Na7- are equally stable. Nope. Na is less stable than Na7-. Na7- has a full outer shell, and Na does not. That's your answer. Make sure you can explain it. And then for the last one, Na7 minus is more stable than Na plus. So now we're comparing two different ones that do have a full shell. Well, what did we say when we talked about radon? Whoever has the most energy levels is more stable. So if we look at Na positive and we look at Na7 minus, who has the most energy level? Na7 minus has 3 full energy levels, so it will be more stable than Na positive. Make sure you can come back and explain that. At the bottom of the page, this is the only thing that won't be homework from these pages. I'm going to go do this with you on Thursday. Okay, so you can put Thursday there. I'm going to do this demo with you on Thursday. Now, in order to introduce the next notes, I'm going to tell you what's going to happen with sodium. When I put a piece of sodium into water, the piece of sodium is about the size of my pinky nail, really tiny, 1 centimeter squared. When I put that piece of sodium into water, it looks like fireworks. It's fire and smoke and sparks and bounces around on top of the surface of the water. So now let's talk about why on earth a tiny little piece of metal reacts with water to create fire. Doesn't seem logical, but it does. It works. So let's talk about that. Why sodium is going to do this. Well, sodium originally has 11 electrons. We just looked at a lot of sodium stuff. Sodium has 11 electrons. It only wants to have 10 because it is one of our stable numbers. What I mean by stable numbers, if you look at the noble gases, we know that they're stable. Okay, so the number of electrons that the noble gases have are our stable numbers. Okay, so our stable numbers, they're right here, 2, 10, 18, 36, 54, 86. Those are the number of electrons that each of your noble gases have. Our noble gases are stable because they have that many electrons. When you have this many electrons, you have 8 valence electrons. The way that there's enough electrons in each shell, this is it. You have 8 valence electrons if you have these. So all the different elements on the periodic table will be ions that have this many electrons because that's how they become stable. So for sodium, in order for it to become stable, the closest number for it will be 10, which means instead of having 11 electrons, it has 10 electrons to become a positive 1 charge, and it is now stable. So if you look at the other atoms in sodium's family, there are lithium, potassium, rubidium, cesium, and francium. None of these atoms have a stable number of electrons. Okay. However, each of them is only 1 electron away from being stable. So lithium starts out at 3, closest one is 2, 19 to 18, 37, 36, 55, 54. Did you notice that each of the atoms on the previous page wanted to lose 1 electron and thus went to a positive 1 charge? This is why they are all in the same column, which is what we call a family. They are part of the same family and they share similar properties, just like you do with your family. Even though they have very different numbers of electrons, all of them have only 1 electron in their valence outermost shell. This is also why they are put into column 1 on the periodic table. Their placement there means they have many electrons, but only 1 of any consequence. Its valence electron. Its valence electrons are the most crucial part about each element. The valence electrons is what interacts with the rest of the world. That's how compounds are formed. That's how reactions occur. So if we're looking at a full board diagram for each one of these 1A metals, for each one of these alkali metals, you see they all have 1 valence electron. Now, instead of looking at the alkali metals like sodium, let's look at the halogens, like chlorine. Chlorine has 17 electrons. Its closest stable number would be 18. So instead of staying at 17, we go up to 18, which gives us a negative 1 charge. If we look at chlorine's family, fluorine, bromine, iodine, none of these have stable numbers. However, each one is only one electron away from being stable. So you look at their elements again. Fluorine has 9, it wants 10. Bromine has 35, it wants 36. Iodine, 53, it wants 54. They're one spot away from the noble gases on the periodic table. They all have 7 valence electrons. Okay, they all have 7 electrons in their outer shell, so each of them only needs one more to be complete. This is why the halogens are in group 7 of the periodic table. By gaining one more electron, the halogens all have a -1 charge. When they become an ion, they all get a -1 charge. So if you look at their Bohr models here. So notice how in group 1, the elements have 1 valence electron. In group 2, they have 2. In group 3, they have 3. All the way up through 8. This leads us to a general rule that chemists use to determine the stability of atoms. The octet rule. The octet rule that says that most atoms will be stable when they have 8 valence electrons or reach a noble gas configuration. When you have the same number of electrons as a noble gas, you have the same reactivity as that noble gas. They're stable. They don't react. Knowing all of this information and applying the idea of the octet rule, you can get the charges for each of our families. All of the group 1 family has a +1 charge. All of the group 2 family has a +2 charge. +3, plus or minus 4, -3, -2, -1. And my noble gases would have a 0 charge. They're not going to gain or lose electrons. So flip open your book to your periodic table, and at the top of each of these families, write these charges. So flip open your book to your periodic table in the very back and write each of these charges on those pages. Your homework will be to complete all of these pages through these questions at the bottom, skipping the stuff for the lab demo. Remember, you won't be in my class tomorrow, so you have until Thursday to complete this.